Hello and welcome back to the Rice Robotics Club Robo-Tutorial. In this video, we'll be doing the final top-level assembly of our robot arm, taking all of the sub-assemblies that we've created and putting it into this final top-level assembly that represents how the robot arm actually moves uh, in our design. So, back in our Onshape document, in the File Select, we're going to create a new assembly. And in that assembly, we're going to insert all of the sub-assemblies we've created in previous steps. There's going to be a lot of assemblies to insert. So hit Insert in the toolbar, navigate to the Assemblies in the dialog box, and just add the base hub subassembly, the base plate, the drive gear, the link 1, the link 2, and the pulley subassemblies. Okay, that's a lot of parts. We're going to make them all together so that they all work as they should in the real world. Hit the green check mark to finalize this selection. Now the cool thing is all of these subassemblies still function as we defined them with all of the mates that we created in each of their assembly studios. Now you don't see those mates here because this is reserved for new mates that we create in this assembly studio. If you hit the drop down of any of these subassemblies, then you can see the parts that make them up and the mates that define their behavior. So even though the mates that we've already created aren't shown here, they're still active. So if you for example, grab this motor, try and drag it around, subassembly moves as a single body because it was fully defined previously. So we're going to move around some subassemblies so we have a little bit of space to work with, and then we'll start connecting things to one another. So the reason we've structured this assembly in the way that we have with several subassemblies and then one top-level assembly is so that every mate that we make in this final assembly represents a degree of freedom of the model, okay? Minus the first one, which is of course going to be a fastened mate to the origin, okay? So we're going to create a fastened mate, going to fasten the bottom of the base hub subassembly to the origin, like we have done many times. Finalize that mate, and this provides just like an absolute reference. This is fixed, and now we can reference it as we position all the other parts of our model. So like I said, we'll be defining the arm's degrees of freedom through the next series of mates. This will be done using revolute mates and gear mates. So we'll have to learn two new types of mates to complete this final assembly. So the first subassembly we're going to add is the drive gear subassembly. This is going to be 1 degree of freedom of our model. So we're going to add a revolute mate. So a revolute mate takes 2 circular edges. It makes those 2 circular edges coplanar, and it restricts all degrees of freedom except for rotation about their common primary axis. Okay, that's a little bit confusing, but it'll make more sense once we get into the mate. Select revolute mate from the toolbar. We're going to select 2 circular edges for this mate. First, we're going to select the circular edge at the outside of this motor. And then we're going to select the circular edge of the hole that goes through the motor shaft here. Okay? Now let's see what that did. If we get in position, first we'll see we actually want this shaft to be going down into the motor. So we'll flip the orientation. But now we'll see that it took those 2 circular edges, it force them into the same plane. And if we finalize this mate, we'll see that it may be hard to show you here. Exit the mate dialog. It can no longer translate, but it can still rotate about that common primary axis. However, we do still have an issue here. The drive gear is phasing inside of the motor, so we're going to need to shift one of those mate connectors so that this mate is correct. Actually, I think we can just do it by editing this revolute mate. So edit the mate, and we're going to add an offset to the mate. And we just need to shift this drive gear upward, okay? So I have that distance already. We'll need to shift it up by 8.7 millimeters so that the motor is behaving realistically and the gear is no longer phasing through it. So specify an offset of 8.7 millimeters. You'll see it actually shifted downward because of the orientation of the axes. So we need to make this a negative offset instead, and it will shift it up by the appropriate amount. And so we will finalize this mate. And now this mate is complete. So we're ready for the next. Before we move on to the next mate, actually, we need to make sure that we name this revolute mate correctly. It represents one of the degrees of freedom of our model, so we're going to name it accordingly. There's a very specific naming convention. If you're going to use a CAD model for simulation, oftentimes you need to name them in this way so that they can be exported correctly. So we're just going to do it as a convention. It's going to be called DOF, which stands for degree of freedom, underscore, and then we're just going to give it a title. In this case, it's going to be base motor. Okay? DOF base motor. And the only degree of freedom allowed here is rotation, which represents the actual motor rotation that will exist in our final assembly of the robot arm. Okay? So now we're ready to add another revolute mate. This time we're going to bring in the base plate. So create a new revolute mate from the toolbar. And we're going to select the two circular edges, the circular edge of the base hub, and then the bottom circular edge of this base plate. Okay? So it makes them coplanar, and there still allows for rotation between the two. If we finalize this mate and we try and rotate, we'll see that it does behave as we expect. Okay? So we also need to make sure we name this revolute mate correctly. Again, it's going to be name, DOF, underscore, and then the title of your degree of freedom. In this case, I'm just going to name it DOF base plate. Pretty straightforward. Now, this is a degree of freedom of the model, but it's not independent, right? So all the way back whenever we started our design here, I'm going to hide the base hub for a moment. We made sure that these two gears would mesh with one another, okay? So these two gears can't rotate independently of each other. How this gear rotates determines how this gear will also rotate and how the rest of the arm rotates, okay? So we need to apply some mate that makes sure that these rotations are always coupled with one another, always associated with one another. So before we do that, we're going to try and rotate this base plate so that the gear teeth aren't intersecting each other. It's not a big deal, but it'll just be nice for looking realistic, functioning realistically. So that looks pretty good. The teeth are no longer meshing or no longer interfering with one another. So we're going to create what's called a gear mate, okay? So a gear mate or a gear relation isn't actually between two bodies. It actually acts between two mates, and specifically two rotational mates, and constrains their rotation in some way, okay? So we want it to act between the base motor and the base plate. And so now we need to decide what the gear ratio between these two gears are, okay? So the gear ratio between any two gears is the same as the ratio between the number of teeth that they each have. And in this case, the base plate gear has 4 times as many teeth as the drive gear. Okay, and maybe we should confirm that that's the case just by going back to look at those gear features. So you edit this one has 8 teeth. And if we look at the base plate gear, it has 32 teeth. So the base plate gear is larger and it has 4 times as many teeth, which means that it will rotate 4 times slower than the drive gear, which is to say every time the base plate gear rotates once, the drive gear will have to rotate 4 times. Okay? So we're going to edit this gear relation. And this relation ratio defines how basically the gear ratio between these two mates, right? So we want this second gear to rotate at 1/4 of the rate of this drive gear, okay? So it's going to have a relation ratio of 0.25. And assuming that I didn't mess up that relation ratio, as we rotate this base plate, we should see, yes, the gears rotate realistically with one another, right? I believe. Let's see. Let's make sure this is all good. Yes, so this relation is realistic. It's what we would expect. But there's a chance that whenever you create your gear relation, they'll actually be rotating um, in the same direction. For example, when I rotate this gear clockwise, this drive gear will also rotate clockwise, which wouldn't make sense because then the teeth would be like passing through each other, and that's not how it's going to work in our actual physical system. And if that is what you have, you'll need to hit reverse direction to correct that. But otherwise, we're good to go here. This gear relation is correct. And we'll go back into our base hub subassembly and unhide that base hub. And now we'll move on to the next part of our assembly. And that will be with link one. Okay. So we need to mate link one, or specifically this servo horn, to the servo body so that the rotation is correctly simulated. Okay. So this is pretty easy to accomplish. We need to create a new revolute mate. One of the references will be the inside circular edge of this servo horn. And the other will be make sure that whenever you're mating link one, it should be on the side of the base plate that doesn't have this block. This block, remember, is to correctly orient the pulley. So the pulley will be here with this servo body, but link one will be here with this servo body. So we're going to mate it to the outer smaller circular edge of this pulley, of the servo body, rather. Sorry about that. And it makes them planar, and it will allow rotation between them, but we need to flip the orientation so that link one is positioned correctly. But now this looks roughly correct. Okay, so we confirm the mate, close out of the mate dialog, and we try and rotate this. So that does rotate exactly as we expect, right? So that's great. There's no other degrees of freedom, no other rotation or translation allowed, which is great. Now you will see that there's some, it looks like this link one is phasing into the base plate, and it is in the CAD, but this is because this is a byproduct of this servo is not the exact same dimensions as the servo that we'll actually be using whenever you construct your robot arm. So we've had to accommodate for that difference a little bit here. So it looks like it's phasing into the base plate, but actually these dimensions are going to be just fine for your robot arm. So this mate is complete. Make sure to name the revolute mate with the correct convention. I'm going to name this one simply EOF link 1. Okay, now we're going to attach the pulley to the other servo. So create a new revolute mate. It is going to be acting, let's see, we have to get a better view of this. First reference is the inside circular edge of the servo horn. And the other is the outside circular edge of this servo. You can see that that's automatically in the correct orientation. So we're going to confirm that mate and test its rotation. You'll see it rotates correctly, just as we expect. Make sure to name that revolute mate with the same convention. DOF pulley. And finally, we just need to add link 2 to the assembly. And to do that, we're going to create a new revolute mate. The first reference will be on link 2. It's going to be this circular edge of the pulley. And that circular edge of the pulley will meet link 1 at this circular edge. Okay? And that orientation looks correct. Don't need to flip it or anything. Confirm the mate. We're going to test its rotation. It's going to be a little bit more complicated because this rotation is going to be happening at the same time as this rotation. I'm going to test it. Oh, it's actually not. Oh, interesting. Okay, cool. So you can see both rotations of the arm work as intended. Make sure to name this revolute mate correctly. Oh, I do that every time. let's see, rename the mate, DOF link 2. Okay, and one final mate is needed. Remember that the rotation of link 2 isn't independent. It's driven by this pulley. So we need another gear mate between the pulley degree of freedom and the link 2 degree of freedom here. Okay? So create a gear relation. Needs to be acting between the pulley and link 2. And in this case, these pulleys are identical. Remember, they have the same diameter, they have the same number of teeth, and they're going to be driven using a timing belt so that their rotations are always going to be the same. So there is no gear ratio or relation ratio in this case. It's just going to be 1, that their rotations will always be the same. So confirm this mate. Now we need to make sure that the rotation is correct. Whenever we rotate this pulley counterclockwise, this link 2 should also rotate counterclockwise. Let's make sure that's the case. And it is. This rotation is correct. Great. Okay, so now our assembly is complete. Have all of our degrees of freedom specified over here. See that we show 5 degrees of freedom, but then we apply these gear mates, and since that locks 2 rotations to be related to one another, that actually removes another degree of freedom. So our final arm has 3 degrees of freedom. It has this base motor rotation, which is responsible for rotating the base plate. It has the link 1 rotation, which is performed by this servo, and it moves this part of the arm. And then it has the pulley degree of freedom, which rotates this pulley, which in turn rotates link 2, allowing for that final 3rd degree of freedom. And that's it. So you'll notice that we did not fully define this assembly. We can move different parts around. And that's just so that we realistically simulate the behavior of our assembly. So make sure to rename the file. I'm going to call this full arm assembly. And the assembly is complete. So well done for making it this far. You've fully CAD'd the arm, and now we're ready to 3D print and construct the robot arm. So I will say there's one more step in the design process before we're allowed to start printing and assembling our arm, and that is tolerancing. And I'll discuss that in the next video. So there's one more step of preparation before we start printing parts, but then we'll be ready to actually start building and implementing our robot arm design. Great job.